So here is a nice picture that I got from Alessandra Nardi. So this person works at Cadence, and this person has made a good slide to explain all these things. So this is a bathtub curve. I mentioned this before. So in the early region, the infant mortality problems may cause failures, and in the later part, it may be the wear out, right? And in between, we may see useful life cycle, right? Useful life, and towards the end, it's aging. Okay. So in the early bird, I'm sorry, not early bird, infant mortality. See, that is where you are worried about quality. We don't want to supply bad parts to the customer. It must be a quality issue because of which the part failed so early. So the idea is to eliminate such bad ICs which can fail so early in the life cycle. Whereas this here is where we are concerned about reliability. So there are standards like AEC Q100 which are addressing that particular issue. And here we are worried about functional safety. So the part may fail, but are we going to take care of functional safety? Okay. That is where these things like failure mode analysis, okay, it's called FMA, failure mode analysis. So those things are becoming important. You may have heard about cloud computing becoming a big thing, right? See, big car companies like Ola and not car companies, big service providers like Ola, Uber, etc. They run fleets of cars, right? The number of cars they run in every city may be in thousands, right? So they would like to monitor all the information about the way this car is being used, how fast the driver drives, are there any incidents that happen, all that information they would like to track. Okay. And typically all that information is uploaded to the cloud. Okay. So there are a lot of sensors in the car. So there may be accelerometers, temperature sensors, pressure sensors. All this is constantly monitored, and periodically they will be sent to the cloud where they can do the analysis. So in addition to that, people are also beginning to practice what is called as edge computing. So there is a device locally which can do a lot of these processing. And I think companies like Tesla are already doing such things. There are two, I think Tesla uses two processors. And if one of them fails, the other one will take over. So earlier I mentioned something called as adaptive testing, right? Now here is, let us say, a question paper that somebody has designed. Okay. Let us say these questions are labeled Q1, Q2, Q3, Q4, Q5. and if you get more than 5 marks in this question, you pass that. Here it is 6, here it is 4, here it is 7, here it is 8. When you actually write down the scores, okay, one particular person may get 6 and pass this, 7 and pass this, 5.5 and pass this, 7.5 and pass this, 8.5 and pass this. The other person is getting 7 here, so he has done much better than the other guy. Pass. He has marginally passed this guy. He again somewhat marginally passed the third question, and this he just barely managed to pass. And in fact, he has failed here. Right? It will be more than 8. He has just got 8, and here he has got marginal pass. Okay. Then how do you compare these two guys? Okay, if let us say you have to consider passing these two guys, do they both pass? Does one fail? Right. In the same way, we may be running a number of tests. Right. We are running stuck at fault. We are running bridge fault. We are running so many different tests, analog tests, memory based. So every chip will get a score for each of the tests that we are running. Okay, and we have to decide on how are we going to grade these chips based on all this information. So we need to grade the chips. In fact, there may be several markets for the chip, right? So where will you send a chip which has this profile, and where will you sell a profile which has this profile? So we may use some sort of machine learning to look at all this kind of information to tell us, how do you cluster your ICs or bin your ICs. There may be one market where reliability is very important. There may be another market where quality is very important. Another one where cost is most important, and things like that. So by looking at all these scores, can you cause reliability clusters, clusters for quality, and so on. And can we order the tests in such a way that bad parts fail early? Okay. In this example, suppose let us consider this guy to be a failure here, right? He should have got more than 8 marks, but he has got exactly 8 marks, so he fails. Imagine if Q5 had been graded first, then the teacher would have rejected him right away. Okay. So it saves a lot of time if you can apply the harder tests first. If your yield, if the yield is very high, right, then of course it doesn't matter in which order you test, but it makes sense to apply hard tests first when yield is not so high. Okay. Also, is it possible to see, suppose we have to employ this guy anyway. See, a company has conducted interviews and this guy has just failed Q5. Okay. But the company may be willing to hire him or hire her, but to be watched. Okay. Somewhere the HR will make a note that this person had just barely managed to pass Q5, so we have to watch. Okay. So all this is called a silicon life cycle management. Okay. There is a term that is being used nowadays called silicon life cycle management. I think we have talked about DPPM, okay, and DPPM is now more like DPPB. I think I have mentioned this already. And another thing you have to remember is the defect may not always cause a fault. it may get masked. Okay. See, for example, suppose there is a stuck at 0 fault here because of some defect. Okay. And in our usage mode, the other inputs are 0. Okay. So you see, even though if this has a fault, you will never know, because we are using this with zeros. Okay. And as a result, that defect never got uncovered during the normal mode. Okay. I am talking about normal mode. In the test mode, we will of course will apply 1 and we will do that. But I am saying, if you are worried about reliability, etc., during normal mode of operation, maybe this fault remains hidden. It's called as a dormant fault, right? So as a result, some people believe that one should go after not faults, but they should go after defects. So there is a term called defect oriented testing. There is a whole conference for this. Okay. But at present, I don't know whether this is being practiced so much. Similarly, is production test coverage sufficient? Okay. All the tests that we do in production tests, such as stuck at faults, etc., they address things like shorts and opens, dust, malformed geometries, all this they take care of. Okay. But later, we may also have things like stress induced faults. When I say stress, I mean thermal stress, electrical stress, vibrations. So those we have to continuously test using in-field testing. And even if that fault were to occur, can we still protect by using safety mechanisms? Okay. So there is a term that is used called single point failure mechanism. If a single point failure occurs, then it's the chip completely fails. Okay. There was nothing else. Imagine that there are 2 points A and B, and to go from A to B, we have many paths, A to C. There are many ways to get here. Maybe these are bridges or flyovers, etc. Then there is a D, and from D you can go in many ways. Okay, but between C to D there is only one connectivity. It may be a bridge or something like that. See, this is very vulnerable. If this fails, nobody can go from A to B or B to A. So that is what is a single point failure. So failure of CD is a big problem. Okay. See, during manufacture, we don't worry about these kind of things. We are sort of looking at all defects in the same way. We don't care whether it is a single point fault, or we are only interested in defects. I mean, all defects. Whereas during usage, we are mainly looking at SPFM. So that will cause a problem. And the problem size is very large. Okay, So I think I mentioned to you about the recalls earlier, right? So in 2011, about 5% of the cars were recalled. That became 15% in 2015, and it became 50% in 2019. So you can imagine how much loss they made, right? Because when you recall a car, um, significant loss to the company. So that is the reason why the companies are worried about these quality issues in electronics. And see, almost 8,000 components apparently get into one electric vehicle, and they are doing all these things: engine control, powertrain control, transmission control, brakes control, suspension control, entertainment or infotainment, sensors. Everything is electronics. So that is the reason why you may have many electronic components. And you have heard about ADAS, advanced driver assistance system. So it is fully based on sensors and algorithms which are trying to find out whether this driver is sleepy, all this kind of stuff. Help the driver in parking. So it uses things like neural nets, artificial neural nets. It may use machine learning. It may use deep learning and all that stuff. And the amount of code that people are writing for cars is apparently in millions of lines. So that is the reason why there are many standards that are being proposed. Okay, one is the ISO 26262 standard for safety of automotives. And the other is what is called as automotive safety integrity level, ASIL. Right, and there are 4 standards: ASIL A, ASIL B, ASIL C, and ASIL D. So there is a concept of severity, meaning what danger is it going to cause, what injuries it might cause to people. Then there is another concept called exposure. That means, look, that problem may be there, but how likely is it to occur? Okay, and finally, can you control the situation? Is the driver able to do something about it? See, for example, if you ask somebody, what if the window gets stuck? Okay, there is something wrong in the electronics because of which a particular window cannot be raised or lowered. What is the severity of that problem? Does it cause injuries? Does it cause discomfort? Can it kill somebody? Right? And secondly, how likely is that thing to happen? And thirdly, if that happens, can something be done about it? Can the driver do something about it? Can you break the glass in case it cannot be opened? Things like that. Right? So there are 4 severity levels. S3 means perhaps very severe. S0 means not at all severe. Similarly, exposure levels, very likely to occur, not likely to occur. And controllability also. It's very easy for the maybe very easy for this driver to do something, whereas C3 may be very difficult. So ASIL A, an example could be both rear lights fail. It's a bad thing. If both rear lights fail, it can lead to an accident. But we consider it as an A. It is not A. First of all, the likelihood of it happening is low because both of them have to fail. B, the severity level may not be so high. There may be other ways. See, it's even though your car rear lights may have failed, the guy who is behind you, that particular car, that person may be using high beam and he still sees you. Okay, So it may be like ASIL A. Whereas the other one is incorrect sensor feedback, meaning the sensor is giving wrong inputs, or also both headlights fail, loss of important data, sensor data invalid. Okay. Brake lights failure. All these are considered ASIL B. Little bit more severe. ASIL C is unintended brake, very severe. Unintended acceleration, very bad. Unintended start, can't even imagine. Oscillation of suspension, bad. Right? ASIL D is unintended steering. Somebody is taken over your steering wheels and they are driving on your behalf. Very dangerous. And unintended braking. So this is very high severity level, and it is somewhat E4 means it's not very likely. It's not so easy to make that happen. And here the controllability unfortunately will be poor, because if the driver can control the steering, he would have done it, but somebody has taken over. So we have to achieve this ASIL compliance, and there are many things that are being mandated. Verification to be high effort, add redundancy in the hardware, use error correction and detection. I think we mentioned about ECC memories, remember? And similarly, we may be able to use what are called as CRC codes to check for errors in the memories, right? Then built-in self-test, we talked about this. Adding watchdog timers is another way. Then you can also add what are called as hardware security checks, and there are some standards for that. Then build fault tolerance. Okay, so errors could occur because of what are called as transient errors. Maybe it's not a permanent thing. Suddenly we may see a 1 and then it may go back to 0. For a short duration there was a glitch, or a particular memory bit suddenly changed from 0 to 1. This happened because of what is called as radiation. Or aging and reliability issues can also cause it. So we talk about, even when that occurs, can you remain safe? So people use hardware redundancy, they use software redundancy, they use code redundancy. So the ECC memory is an example of code redundancy. We are using parity bits, right? Extra parity bits. Hardware redundancy, an example could be using two processors. Okay, in Tesla cars, they use two processors. If one of them fails, the other is available. Similarly, you can use some redundancy in software. So you can do two different algorithms to calculate something. See, for example, you are trying to find if there is the car is moving through some terrain, and you see some sort of a road sign. So you are deciding whether it's a road sign. Does it mean brake? Does it mean children crossing the street? Something like that, right? So there is a software which is coming up with this decision as to what this road sign is. So you can have two different algorithms for determining. Okay, there are multiple image processing algorithms which are available. So run two of them, and if they both agree, use that one. See, if you want full security, then you should use what is called as vertical integration. Vertical integration means you do everything. Okay, the IP, all the IP you develop, you only design the hardware, you only design the software, everything. You are see, some companies are doing this, isn't it? I think an example could be possibly Apple, right? Although I think they don't manufacture their own chips, they go to maybe other parties to make them. But you see, Apple will make their own hardware design, their own software design. They probably design their own IP, right? But it is very difficult to do this. But when you are not, when different companies are working on a project, if you want to achieve the same effect as vertical integration, there must be free flow of information between companies. They must be honest in sharing the data. That is the problem. So ASIL is very closely related to self-test, right? So we need to find as quickly as possible if something is wrong and what is wrong. And the challenges in that is that chips are very complex nowadays, and cars have a long life expectation. Maybe people use their car for maybe 10-15 years, maybe more. See, it doesn't mean that the same person will use for 15 years. So it may go from one owner to the other. Somebody will use the car for maybe 5 years and sell it off, but that car will continue to be used for another 5 years, and then there may be a second the second buyer may sell it to a third buyer. Okay, those things don't happen with things like mobile phones or laptops, right? Whereas for cars, it is still like that. So security attacks, right? I think you may have heard about how people are stealing, credit card numbers. You may have heard that people can, if you are keeping your credit card in your pocket with some external device, they can come and steal your credit card number and your PIN, etc. Okay. Similarly, people can steal IP. They can steal trade secrets, right? They may produce fake copies of the device. They may do a denial of service attack. They may control the car remotely. They may take control of a industrial robot remotely. All this is very dangerous, right? Unfortunately, all these are happening, right? So testing will also have to play a role, okay, to see if there is any Trojan in the chip, right? We can test it for defects, etc. But in addition to that, maybe we can look at whether safety concerns are there, Trojans are there, etc.